If there's next to Earhart, WoW is in the same.
Yeah, okay.
Next to Earhart, last semester, there was this. Yeah, I think it's back. I was gonna go see if there's
Everything is closed. Like, I need to start actually using my blocks because I'm used to like less than 5 blocks. I've been here for like 2 weeks. So I've been here for 2 weeks, but we've only had like 1 week of the plan being active because they don't go live until the 30th. But I'm gonna use all the ones I got. I gotta start actually eating more than like 1 meal a day. And stuff like that. It's like I really classes, so I don't want to go get breakfast, and then it's like I have classes until like now, so I can't really get lunch. So it's basically like go get food right after classes, and then maybe get food. Unless I'm gonna wake up earlier and I already need to get breakfast, which I really don't. I'll focus on Arrow 1 and Arrow 1 quizzes. That's basically the rest of my day today.
Yeah, I have a couple of things. That the one I talked about. I've talked stuff with student union, see if I can get the department student engagement to improve the meeting.
Okay, everyone, welcome back. Get ready to take in-class attendance. Good time? No, not yet. Sorry. You still have 2 more minutes to chat. Continue. Sorry about that. Not 1 yet. Well, not yet starting time, but do you have any question? Well, go ahead if so. We still have time though. You got any question? Go ahead, Robert. Right, yeah, I don't want. Go ahead.
No, I don't.
You don't what?
I don't have a question.
You don't have a question. Appreciate your compliment. Go ahead, Dylan.
For quiz 1 and quiz or 1A and 1B, do you have what?
Oh, somebody's online. Can you hear us? Okay, good. So let me just mute you. Oh, sorry. So if you want to say something, unmute your microphone, start talking. Okay. I hope you're hearing it. Okay. All right. So 1 person online today. So go ahead, Dale.
Do you have a paper saying what is standard units so when we do the quiz we can convert? Because in some classes,
do you have what?
Like PSI is standard in one class, but you were saying here.
PSI is never be standard. Who the hell said it? I want to know the name. That person is wrong. PSI is not a standard. Didi, I mean it. Who the hell actually said it?
Reiner, for real. Talk to him.
I'm gonna talk to him. It's not the standard. Inch is not the standard. Don't use inches in your calculator.
Anyway,
You're gonna make a mistake. Somebody die and you'll be pointed a finger at. Don't do that.
can you give us what is standard for each
Sure,
one?
sure. Let's just go back to the notes that we covered in last class. Okay, that's the best way to start. I'm gonna talk to him. Don't worry about it. Let me handle that. PSI is not standard. So here we go. So this is standard unit. Stick with engineering. Okay, arrow 1. Okay, sorry. So PSI, I never use that. Where's PSF instead?
It's
Pressure. Okay, here we go. This is standard. PSF. No. PSI, you have to convert it to PSF. It's not kidding. Okay, you might be smiling here, but I'm dead serious. People misunderstand that kind of basic things. That's why people die. All right, it's not joking. If I need to correct a professor, I'm corrected. I'm an engineer, okay? So don't believe PSI is the standard. Whoever said it, it's wrong. I can take it to the court and squeeze out the money out of it. You said wrong thing. Right. So this is PSI. Of course, foot is used always. Now the danger of using PSI is, of course, you keep using inches inside of your computation and ended up having wrong result, and you never know because your argument is, well, I used inches throughout my computation. What's wrong with that? A students always do that. Okay, because they're so consistent, and they don't believe they made a mistake. But pound force can never be created from inch. You need to have foot. Suppose if you have a problem involving combining certain things to create the pound force out of it. Okay, do you remember the last class's example problem? If you use inches, you can never create the pound force out of it, right? You need to have foot. Because pound force by definition, okay, slug, not the pound mass, slug, foot per second squared, okay? So don't stick your pound mass number in it. Don't stick your inch number in it. You're going to make a mistake. No matter how consistent you want throughout the computation, you're going to make it wrong. So PSI, it's not the standard unit. Of course, there's a reason why people stick with PSI. Do you know the reason? Go ahead.
Easy numbers.
Because it's easy numbers. If you use PSI, it's huge. Who wants to deal with 2,000-ish numbers? You want to have a 14.6. That's PSI. Numbers are reasonably good range you can handle in your calculator. That's the stupid reason why people think and use non-standard unit every day. You're not an engineer, don't do that. Every calculation, as long as the number you type into your calculator, it must be standard unit. You're using it without knowing or realizing what you're doing. From now on, you know what you're doing. You're consciously thinking, hey, this is inch, I know I have to convert it to foot along the way. You naturally do that. Before, you didn't know why you were doing it. Now you know what you're doing. That's a big difference out of this class. So PSI, people use that all the time, but when you pick up the number associated with PSI, you have to once convert it to PSF no matter what you go. Then after computation, PSF result is associated with the number. Your professor wants, well, I need a PSI, why don't you just convert it again? So twice conversion process always involved. Okay. Go ahead.
Do you mind?
Just close the door. And I gotta take attendance, though. I'm not gonna keep
Do you
going.
mind, like you have Pascal as the standard, do you mind if we use kilopascal or megapascal?
Kilopascal is 1,000 Pascal, and then knowing Pascal is Newton per meter squared, this is standard, you can use Pascal, of course. It's the same thing, Pascal is Newton per meter squared. Go ahead.
It's 14 PSI, right?
14.7 PSI,
14.
standard sea level, atmospheric pressure at the sea level.
Okay.
That's right.
Okay.
But we're not gonna use that number, right? Go ahead, pick up a calculator, 14.7 multiplied by 12 squared. Go ahead, do that.
Yeah.
Did you get this one?
I got
this
it.
one? Okay, good. That's what you do always. Because 14.7 is not the standard. Before you move on, you convert it to this. And then pick up that number for the rest of your computation. So always pre-process is involved, right?
So in the quiz, I would use pound as just regular pound.
Which pound?
I know, but like,
Pound mass or pound force? Which one?
No, because like I would mention P. I'll be saying LB
Again,
for
which
pound
pound?
mass.
Which pound?
Pound
That's
force.
Pound
Yeah.
force, okay. Good.
I noted that pound is pound force, but
Okay,
when I meant pound mass, I would write an N
okay, good.
because it would confuse me. With
Oh, yes, that's good.
Okay, so just making sure.
Okay, you're getting there. Okay. So if somebody say pounds, you wanna know, is this pound mass or pound force? Because it matters, especially for this quiz one. Oh, yeah. I hope you're doing it. Well, pounds are pounds, what's going on? I mean, you get 0. Okay. I'm not going to give you any partial credit for quiz 1 if you behave like that. This is aerospace engineering and aerocraft. What are you doing? Kind of thing. Okay. So let's just set all the units straightened out. That's your first step of this class. If you cannot do it, you can never go through this class. Okay. You can take this class from someone else. I don't care. All right. By the way, next semester I'm not going to teach this class. Oh, good. Good news? I don't know.
Wait.
No.
Wait.
Next semester I'm not going to teach this class. Next semester someone else is going to teach AE301. You can take this class from that person if you want to. I don't mind. Okay, well, let's just stop being the enemy of students, you know? That's not my purpose here. So hopefully you understand, straighten out the meaning of units. That's very important. Very important. I cannot overemphasize it. Unit is everything. If somebody die in the future because of your stupid mistake, that's going to be, I can guarantee, unit mistake. Don't do that. Okay, let me just take this. Attendance, ready to go? Let's move on. Okay. All right, good. Let's just go quickly. I'm spending too much time.
I'm in AE301 today.
I'm not a teacher. I'm a teacher. There we go. Good. And yeah. Okay, good. Let me double check.
Try turning it on.
All right, looking good. I'm done. Participation, attendance. All right. So it looks like 2 people online today. Let's say hello. Say hi. Say hi.
Hello.
I can hear you. Say hi.
Hello.
Hello.
Okay, good. So if you have a question, just don't hesitate. I'm going to mute everybody, but you can unmute your microphone, ask question anytime. All right. Okay, so today we are going to continue on Unit A1. But before that, let's just take a look at updates. You guys all know, should all know updates. So what's coming up? Whoa, looks like it's tomorrow before noon. Tomorrow, right? Today is Wednesday.
Yes.
I hope you're working on it or you're done already. I really hope. If this is your first time looking at it, oh my goodness, you're in trouble. I hope you know. Okay. All right. So quiz 1A, quiz 1B is entirely based on problem 1A and problem 1B of quiz 0. So first of all, don't skip this process. You're going to regret like hell later. I can tell you. Don't skip this process. Finish up quiz 0 problem 1A and 1B. Then and only then you work on quiz 1A and quiz 1B. Don't skip that process. I can guarantee that you're going to regret it if you skip through those things. There's no way, okay, you can play games in this class as long as I'm teaching. Either you get your real skill, you cannot pretend. This is engineering. I'm serious. I'm dead serious. Okay, if you don't like me, well, of course, lots of people don't like me. Of course, I know that. You can avoid it, of course. You have lots of plenty of other options, you know. I'm Japanese. If you hate Japanese professor like this, you know, you can do something else, of course. But as long as if you want to pass aero, I expect you to have a real aero skill. That's what I want, starting from here. So today I'm going to continue on Unit A1. I'm thinking that I'm going to probably finish up A1. If so, the homework due is going to coming up. So let's just talk about that toward the end of the class. Stay focused. If you want to go sleep, I mean, you're going to pay the price for it. Okay, so let's move on. So A1. So we talked about engineering units. These are the standard units we are going to deal with in aerodynamics class. Obviously, I'm not going to use PSI. If somebody gives me PSI, I'm going to quickly convert, first of all, to PSF, then move on from there. You should do the same thing as you work on quiz 1, A and B. Okay? Pre-process to begin with. then use only the standard units associated values in your computation in your calculator, and then after you get the results should be all based on standard units. If you want to have some specific units later, you can convert it back again to get desired units. Twice conversion process. Pre and post processing is always involved in your computation. Okay, so let's move on to next page. So in this class, AE301, of course, this is basically picture taken from wind tunnel. Okay, have you ever seen this kind of? Have you seen this kind of thing in fluid mechanics? Fluid mechanics. What's this? This is wind tunnel. What kind of wind tunnel is this? Have you ever seen it, or touched it, used it, whatever, what not to? This is called smoke wind tunnel. Have you ever seen it? I usually show the video at the fluid mechanics class. Hey, this is smoke wind tunnel. Have you seen that kind of stuff? I hope so. You have a mixed response. So this is, by the way, video. This is video. Let's keep going. Do you believe in it? This is video. No, I'm kidding. This is picture, of course. But you can never tell the difference between picture and video. What kind of flow field is that, if so? Steady state. And then laminar flow is, of course, steady state flow to begin with. If it's turbulent, obviously, it's not steady. Yeah. Yes, that's right. So this is laminar steady state flow field. In other words, this is a still picture or movie. I cannot tell the difference. Flow field never change over time. So that is something we are going to start with in AE301 because it's so easy and we can simplify mathematical analysis for that. Okay, so we are going to talk about how to represent flow field in AE301. Do you remember flow visualization concept in fluid mechanics? We have 3 different kinds of concept. Number 1, people talk about path line. What is path line? Oh, is it different from streamline?
Isn't it path line?
What is path line? Yeah.
Path line is like where your fluid element travels. But a streamline, it's the same thing as long as you know streamline is.
It's the same thing, but it's not the same thing.
It's only the same thing when the streamline is follows the path line.
That's right. When does that happen?
During steady state.
Steady state. Okay. So in fluid mechanics, hopefully you are exposed to 3 different concepts of flow field visualization. One is a path line. Is this a path line?
Yes.
Yes. Yes. Yeah.
It's not. Okay, anyways. The other one is a streak line. Is this a streak line? Yeah. Yes, indeed. This is a streak line, it's not a path line. Why is that? What's the difference for those two? Well, of course, fluid mechanics concept. Now, path line is if you release a single particle, that single particle take the path. That's path line. This is a line made up by multiple particles released in single spot. That's called streak line. This line is made up by series of lots of different particles released at the single spot. That's a streak line. It's basically ink, streak of ink. If I have a pen creating a streak, this is a streak line. Okay. So you're seeing streak line. The path line, I cannot really see it. Suppose if you release a small tiny particle here, that particle moves around along this. If you see that kind of stuff, it's called path line. Path line is usually not easy to visualize. You need to have a special device or something. Go ahead, Daryl.
Since it's steady state, isn't that also a path
If it's steady state, those are all the same. That's what you're saying from fluid mechanics. It's correct. And then third concept is a streamline. What the heck is that? So now you know the difference between path line and streak line. This is a streak line, but at the same time, this could be path line. Okay, if it's steady state. Question: is this a streamline also?
The whole thing.
Not the whole thing. Do you think this is a streamline?
No.
No. How about this?
No.
No sense. No, those are not streamline. This is kind of. This is yeah. This is yeah. This is yeah. What makes the line streamline? Steady. Streamline is a mathematical concept. You can represent a line within a flow field where that line represents the direction which is tangent to the velocity component at each location. That's called streamline. Streamline is a pure mathematical concept. You can define equation of streamline in the flow field, but flow field must be steady. If the flow field becomes unsteady, you define stream. No, you cannot. Mathematically speaking, that's a turbulent flow. Math is probably a million times more complicated than steady state. So let's just set those concepts straight out. By the way, this is nothing new. It's coming all straight from fluid mechanics. So if this seems to be your first time hearing such a thing, go back to your fluid mechanics notes. Or you can take a look at my fluid mechanics notes. Either way is fine. Okay? So in aero, we are going to focus on streamline because it's a mathematical concept. Do you guys know the equation of streamline? Anybody? Go ahead, try. Have you ever seen equation of streamline? Okay, I'm going to let you derive it for the upcoming homework. So wait and see. So if you don't know the equation of streamline, just go rush back to your fluid mechanics. Or take a look at my fluid mechanics notes.
Is it from Bernoulli's?
No. Equation of streamline. I'm not going to cover same material over and over. This is aero class. If you don't know what I'm talking about, go back and find out. Equation of streamline. Is there such a thing? Yes, we do. We're going to start from there because otherwise, how can we analyze the flow field? Okay, aerodynamics uses mathematics to analyze the flow field. Starting point, the simple starting point is picking up equation of streamline. Do you guys know that? If you guys don't know even the equation of streamline, where do I start? I don't know. Go back and find it. And then if it's possible, go ahead, try to derive it. Coming from what concept I can get equation of streamline? Okay? So those are streamlines, sorry, because this is almost steady state. Okay? Now, if you draw a perpendicular path between those two streamlines, now obviously the velocity changes from point 1 to point 2. Obviously something is involved. It's called viscosity. Velocity changes in a perpendicular direction over the surface. Now, here's a pop quiz. What is the velocity right there on the surface? Zero. What do you call that?
Stagnation.
Not the stagnation point. It's a non-slip condition because of the viscosity. So velocity starts from 0 over the very same layer, keeps changing to the value you measure at the edge of it. This is called boundary layer. You've heard of it? Boundary layer is formed up because of the viscosity present. And then within the boundary layer, because of the viscosity, you're going to develop shear stress present. Now, if you measure the shear stress tau right on the top of the surface, it's called wall shear stress. Wall shear stress is the source of skin friction drag of airplane. Okay? Everything comes from fluid mechanics. By the way, what kind of equation is this? Have you ever seen that? Fluid mechanics. What kind of fluid behaves this way?
Newtonian fluid.
Newtonian fluid. Linear relationship. Linear relationship between velocity profile to shear stress through this property. What's that?
Viscosity.
This is called viscosity. Dynamic or absolute viscosity. Okay. So we're not going to talk much about boundary layer in Aero 1. It's the main subject of Aero 2, viscous fluid flow. But we're going to touch base on flat plate boundary layer, which is unit D2. At the very end of the semester, if you survive through it to that point, we're going to touch base of boundary layer so that we are going to make you ready to go to Aero 2 Okay? Most of the time in AE301, we're gonna basically ignore the presence of viscosity and then boundary layer. What kind of flow field if I do such a thing? Inviscid flow. Viscosity 0, no boundary layer. If the flow field is inviscid, flow field is governed by someone's equation. What is it? Let me repeat. If the flow field is inviscid and steady, equation governs the flow field. What is equation? Go ahead, say that. No. Thank you for your wrong equation. Wrong answer. I appreciate that. No, not the Bernoulli. Bernoulli requires one more assumption. Euler's equation. Euler's equation is basically a governing equation of steady, inviscid flow field. Oftentimes you already ignore the gravity because it's aerodynamics. Steady, inviscid, no body force, zero gravity flow field is governed by Euler's equation. Of course you know Euler's equation from fluid mechanics. Go ahead.
Isn't the additional condition to turn Euler's equation into Bernoulli's equation?
That's
that
right,
the fluid has to be
incompressible.
incompressible?
That's right. Density constant added to Euler's, you get Bernoulli. So we oftentimes go back to Euler's equation, Bernoulli's equation. I actually try to derive it once again, and then we're going to start from there. All right. Next page. So those are the properties we are going to create within a flow field. Pressure is P, lowercase. Density is rho, lowercase. Temperature T, this is temperature. Now, those three things, pressure, density, temperature, those are related. What kind of relationship do you know? Go ahead.
There's ideal gases.
Ideal gas equation of state. Pressure equal to rho RT. R is involved, gas constant. In case of air, we use the specific gas constant for standard air, 287 joule per kilogram Kelvin, or 1716 foot-pounds rad ranking. I kind of know the number because I use it over and over again over like the 40 years. I know those values, but of course you should. Those are specific gas constant of air. This is the velocity. Velocity is different from others. Velocity is a vector quantity, so you have component-wise directional components. X direction component, Y direction component, Z direction component. You're talking about X, Y, Z Cartesian 3D. You have to deal with, this is always a vector. So whenever you see an equation, some equation could be a vector form. That means you look at single equation, but equation can be broken down into three different components, depending on the coordinate system you're talking about. Of course, you know that. What kind of equation you're talking about? In fluid mechanics, linear momentum equation. It's a vector equation. Do you remember those things? Linear momentum equation is not the single equation because it's vector. You have components. If it's 2D, you have two components. If it's 3D, you have three components. Can you handle those things already? Of course you should, because that's one of those quizzes. And then oftentimes we do use inverse of the density called specific volume, lowercase b. How do you get inverse densities, specific volume? Volume over mass, that's right. So suppose if you're given a volume of air divided by mass, if you know such a thing, then you can get specific volume, which is inverse of density. Okay? Oftentimes, we don't talk about density. We talk more about specific volume. We want to talk about compressibility of a flow field. It makes more sense to talk about specific volume than density. You say density stays constant is incompressible from fluid mechanics sense, but let's just take a look at once again in aerodynamic sense. Does it really make sense? Let's talk about specific volume instead, okay? We're going to talk about that later in Unit A3. And also, of course, PSI, PSI A, PSI G, absolute pressure versus gauge pressure difference. You guys know those differences. How do you convert absolute to gauge? Do you guys know the equation?
P absolute is equal to P atmosphere plus P gauge.
Not really.
No?
No. Anybody else? Not really. I don't do such a thing. So let's draw a line here. This is a zero absolute. What's zero absolute? Zero absolute pressure, what is it? Can you create such a thing? Not really. It's theoretical. If you can create the perfect vacuum, no absolute, no nothing, it's zero absolute pressure. So everything's measured from there. That's called absolute pressure. Okay? Then you have something called PATM, atmospheric pressure. This atmospheric pressure depends on where you are. If it's sea level, do you guys know the value?
2116.
Correct, or 14.7 psi, or 2116 point something psf. Okay, 760 millimeter Hg. Anyways, so PATM depends on where you are. Do you think right here in this classroom it's still 14.7 psi? No, this is 5,000 feet altitude. It's probably 12.8 psi or something like that if it's standard there. This is how much gauge pressure do you measure from this line? This is called zero gauge, classic definition. Zero gauge, not the zero absolute. P atmospheric pressure is zero gauge. So if somebody says PSI G, depends on what kind of gauge you're using. If you're using pressurized gauge, pressurized tank, okay, you stick on the pressure gauge to the pressurized tank. If it says 5 PSI G, it's here. PSIG, pressurized tank. If you go visit the supersonic tunnel, supersonic wind tunnel is connected with a vacuum tank. If the vacuum tank says 10 PSIG back, what is the absolute pressure? It's this one. This is a PSIG back. So it depends on what kind of gauge you're using. So vacuum gauge is a reference to the local atmospheric pressure. That's why it's called zero gauge pressure. P atmospheric depends on your location. Okay. So how do you convert, let's say minus 5 PSIG or 5 PSIG back into absolute pressure? You're going to subtract that back. Okay, and then of course you know what is PATM in this room. You need a device, something called barometric pressure gauge or something to determine exactly what's PATM in this room. So if you're looking at the gas tank and pressurized, ready to explode, and then it says 25 PSIG, are you going to add or subtract? You're going to add to the local atmospheric pressure to get absolute pressure of that tank. So it depends. Do not memorize equations. Picture this. This is the concept of a gauge pressure and absolute pressure difference. Okay? Memorization, I don't welcome that. Because memorization usually means that I have no clue, but I try to memorize anyways because I want to pass this exam. It's not going to work here. It's not going to work here. Either you get the concept right, know what you are saying or doing. That's the only way. Otherwise, you can't go through this class. Okay? So I actually appreciate that because that's typically what the professor says. Hey, this is the equation, memorize it. No, no, no. This is the concept where those equations come from. You grab that. Not the equation. Equation, if you need it, you can derive it anytime. That's what you need to be doing. I force you to do. In this class, you'll be tasked to do lots of equation derivations. So think about this. If I know the concept, I can derive this equation anytime I want to. That's the skill set of engineer. I want that. I'm not going to usually give you equations. Plug and check is over in fluid mechanics. Okay? You're not going to do plug and check. If you cannot even derive your own equation, there's no way you can plug and check. Okay. Having said that, those are the concept of, okay, so pressure, be careful about the absolute versus gauge, obviously. Do not use gauge pressure inside of your computation. Usually not good. Usually not, well, actually very bad for quiz 1 and quiz 1A and 1B. Only use absolute pressure, not the gauge. Okay. Yeah.
Sorry, I'm just so confused. So, if it's given the atmosphere pressure,
Let's
then
let's
you-
just Robert, let's just do it later. I can walk you through it. Okay, just send me text and let's just get connected. Let me move on. Okay, density or specific volume. Okay, so those are the standard units. If it's density slugs per cubic foot, I'm not going to use pound mass. Now, oftentimes, if you take thermodynamics, pound mass is given for your information property table. You know why? Because the numbers are nicer. Don't pick up those numbers, use it as is inside of your calculator. Always convert it to slugs. Thermodynamics. Okay? Now in Aero, I know that, so I'm not going to use pound mass to begin with. I always give you value with slugs. And inches, of course. I'm not going to give you inches. So this is a standard unit for density. If it's a specific volume, it's a cubic foot per slug. Okay? Temperature. Do not use relative scale temperature such as degrees C, degrees F, because those are essentially the same thing, measured from some relative value. Similar to this atmospheric pressure, typically you're not going to use that. You're going to convert it to absolute scale temperature to begin with. Okay, so let's be extra careful about those. Velocity is a vector, so you need to be careful about that. You're not going to mix up vector and scalar in single equation. Don't expect any partial credit. I'm super picky about that. If the equation is a vector equation, treat it as a vector equation. I'm not going to allow you mixing up those things. That means I assume that you don't even know the concept of vector calculus. You should go back all the way to the calculus class. Okay. So lots of things to catch up in this class. At least at the very beginning of the semester, I'm probably driving you insane. You need to go through it. Okay? You need to go through it. That's the only way. Let's move on. By the way, those are the vector notation. Now, in class and handwriting, I always, if it's vector, I always show it as a vector. So handwriting, typically, this is the vector quantity. This is handwriting way. Oftentimes in textbook, the vector quantity is like a bold typeface so that you can tell, hey, this is vector quantity. Be careful about that. But in handwriting, it's very difficult to do. So I usually go with that. This is handwriting vector. Okay? Oftentimes, space people do like underline. When I took spacecraft orbital mechanics when I was a graduate student, the professor of that class kept using underline. This is a vector. I said, whoa, that's underline. We never use such a notation in Aero. Well, I don't care about Aero people. I'm ASCO kind. Anyways. But sometimes people use this kind of notation. Be careful about that. Get used to it. Those are the unit vectors. Okay, unit vector for Cartesian is very special. I, J, K. And then I usually do tiny hat on top of it, representing this is unit vector. What is unit vector, by the way? Anybody?
Vector with magnitude of 1.
It's a vector with a magnitude of 1. Okay, that's unit vector. Now, those are the unit vectors of, let's say, cylindrical coordinate system, ER, E theta, EZ. This is the direction R, theta, Z, magnitude 1. Okay? Do you guys know one more coordinate system that we never use in this class? Spherical coordinate system. We never use it in Aero, but you probably end up always using it in astro class. What is that based on?
Rho, phi, and theta.
Okay, spherical coordinate is, okay, what is this angle? What is this angle? What is the distance to the satellite? Spherical coordinate. It's all coming from that. Cylindrical is you have axisymmetric body, like a fuselage of an airplane or something. This is a Z direction. And then if you take a look at cross section, this is the theta, and this is R kind of thing. So it's from there. Cartesian, of course, X, Y, Z. Okay. So each time we're going to represent the vectors in proper manner. Now, by the way, if you want to take a close look at that kind of stuff, I would recommend you go all the way to Unit B1, Mathematics for Aerodynamics. This unit actually covers tons of basic math in which this is 100% YouTube. I'm not going to lecture in class. You don't have to wait for me. Go take a look, okay? All right. So let's just move into next page, equation of state. Equation of state is heavily involved in your quiz 1A and quiz 1B. Of course, quiz 0, problem 1A and 1B. Obviously, equation of state relates pressure, density, temperature through a gas constant. If you're talking about air, air is a gas constant, which is, those are the values. This is called specific gas constant, in this case, air, standard air, okay? It is coming all the way from universal gas constant divided by molecular weight, or this is molecular weight. So this is a universal gas constant, and air comes in with specific molecular weight. So you're going to come up with air specific gas constant. If you're talking about nitrogen, nitrogen comes with different value. Very similar to air, but it's kind of different, okay? So when you talk about quiz 1A and 1B, don't use those values, of course. Space Shuttle's landing gear is not filled with air, it's nitrogen. Nitrogen comes with different values of gas constant. Be careful about that, okay? Now, those are based entirely on standard units. You can use this value as is in your calculator, okay? Now, important thing is, let's just talk about equation of state. Equation of state is an important equation. You can relate pressure, temperature, density, okay? Here's an important question as you look at quiz 0 problem 1A, 1B. This is actually interesting question coming typically from non-engineering type person. Okay, I went to Phoenix today. I went to car mechanic, and then car mechanic filled up my tire with a very nice pressure, 36 psi, perfect. And then there's absolutely no leak. Tire is perfect. Mechanics perfect. Filled up with a perfect pressure. Then I was driving back all the way to Prescott. All of a sudden, no tire pressure comes up. Wait a minute. Is there any leak? No, there's absolutely no leak. What's going on? Pressure stays constant if there's no leak. I mean, that's a very classic misunderstanding. Do you agree as an engineer? If there's no leak, pressure stays the same. No way, because temperature may be different. And then volume, because of the temperature difference, volume may change. Because you drive a long distance, the tire volume may change. If the volume changes, the density may change. Okay? If the density changes, pressure may change, of course. One thing, only one thing remains constant if there's no leak. What's that one thing? Anybody?
Mass.
Mass. Why?
It's how much stuff there is if nothing's leaving.
It's called conservation of mass. Do you remember that from fluid mechanics? Okay, that's a big hint. Only one thing remains constant: mass of air inside of the tire if there's no leak. Conservation of mass principle. Anything else could potentially change. Anyways, so that's a big hint as you tackle quiz 1A and 1B. So classic mistakes for those quizzes. Well, pressure should stay constant because there's no leak. You get 0 out of 20 if you believe in that kind of stuff. Okay? You're an engineer. Obviously, that's not right. But mass stays constant. The only mass stays constant. Okay? So here's an interesting thing. So P equal to rho of T. You're going to apply this equation to solve that quiz 1A, 1B, and also quiz 0, problem 1A, 1B. P equal to rho RT, right? Or since density is inverse of that, so that you can say RT over lowercase b. Look, b equal to 1 over r, or rho equals 1 over b either way. Okay? So you can do that. This is specific volume. You can do that. Now, when you use this equation, you must be very careful about pressure here. This must be absolute pressure, not gauge pressure, okay? Temperature here, this is also absolute scale, not relative scale. Be careful about that. Gas constant, 287 joule per kilogram Kelvin.
That's for just air, right?
Yeah. This is Newton meter, that's joule. Or 1716 foot-pound slug ranking. Make sure, okay, all the units cancel out and line up. In other words, within the same equation, unit on your left-hand side, unit on your right-hand side of your equation must exactly match up, otherwise it's guaranteed wrong analysis. Okay, this is a unit problem, quiz 1A and quiz 1B. A unit problem, you show all the units of your numbers. Otherwise, I'm not convinced. If you make some mistake and not showing units, don't expect much partial credit. This is a unit-focused problem. You show all the units, your all numbers. Everything you show with a number, show all the units. Okay, please do that. Question, Robert?
Yeah, it's
Right.
not good to just put joules. Like
Joule is Newton meter.
Yeah, but is it better to?
Joule is a standard unit like a Pascal. Okay, you can use joule, that's fine. Any other question? Okay, so in aerodynamics, we are going to talk about different kind of ideal gases. First one is calorically perfect. Oh my goodness, what's the one? Calorically perfect. Or thermally perfect ideal gas. Those are ideal gases. Okay, so wait until we cover unit A3. We're going to talk about two different types of perfect gases or ideal gases. One is calorically perfect ideal gas. The other one is thermally perfect ideal gas. How many people actually have taken thermodynamics? Can you tell the difference for those?
One is based on the pressure of water.
No. Okay. Do you guys remember specific heat?
Yes.
Yeah.
That's
If the specific, what's the specific heat, point one? Okay. Yes means you understand perfect. Well, specific heat is a property of a substance. How much energy you need to raise a temperature of this substance. Let's say air has its own specific heat value. How much energy do you need to see the 1 degree change of temperature of air? That's specific heat. Now, if the specific heat is constant throughout the flow field, it's called calorically perfect ideal gas flow field. However, specific heat depends on also the temperature you are in. In a high temperature zone and low temperature zone, specific heat might be a different value. If so, it's called thermally perfect ideal gas. It is still perfect ideal gas, but you have to take extra care because specific heat value is now a variable. Now, thermodynamics, have you ever looked at specific heat as a function of temperature kind of table? Do you remember those things?
Yeah. Yes.
Oh, that is thermally perfect ideal gas. If the specific heat is constant, it's called calorically perfect ideal gas. Which one do you like better? Anyways, easy ones. Right? Now, we are running out of time. I couldn't finish up unit A1. That means I cannot say, hey, turn in homework tomorrow. No, you can't, I can't do that. I haven't done this example A1 too. So, but don't wait until I announce homework due date. Okay? Take a look at this problem. And then after I complete this homework, A12, of course, you can basically start doing homework assignment A12, A, B, C, D, E. Homework A12 is based on classroom example A12. Go ahead.
So as of now, we have the knowledge and materials necessary to do
I
A11, but not A12.
Well, I'm not sure. You can take a look at each problem. I guess you can probably solve it.
Based on where we are in the lecture.
Just where we are is I haven't done classroom example A12.
Got it.
So I cannot say, hey, turn in homework next day. Well, I cannot do that.
So for the mandatory self-learning materials,
Yeah.
do you want us to start watching those now, or would those be like an assigned thing later?
You can do it anytime, but I usually try to tell you, okay, now is the time, take a look at this YouTube video kind of thing. Now, this unit A2, I want to spend some time, okay, going over the hydrostatics of fluid mechanics.
Okay.
Because this unit is entirely based on fluid mechanics hydrostatic equation. I want to spend probably next class reviewing over that.
Okay.
And then I'm going to tell you, okay, take a look at this. Okay. Any other question?
What?
Go ahead.
Just kind of a scheduling thing.
Yeah.
After we complete the second problem for unit A1, then we're going to move on to hydrostatic pressure equations after that for the next class.
That's right. So next class, I'm going to finish up in-class example A12, of course, and then finish up A1.
Okay.
Then I'm going to announce, okay, turning homework such and such a day. I'm going to announce that homework due date, which is kind of negotiable. So you can say, oh, no, we cannot do it's negotiable. I'm flexible. But anyway, then after that, I'm going to go over fluid mechanics hydrostatic equation. Then after that, I'm going to probably tell you, okay, go ahead, YouTube video, then we're going to start doing A3. Because A2, I'm not going to do in-class lecture. I'm going to jump right into A2 after that. Okay? A2 is 100% YouTube. That means you can do it anytime. Yeah?
And I'm willing to bet that video contains all the stuff we need to do problems A12 and A22. Obviously.
That's right.
Okay.
That's right. You're right. Any other question? Go ahead.
So when we turn in the homework, are we turning in A11 and all the A12s?
Well, I'm going to tell you, first of all, turn in homework of unit A1 to begin with.
Is
Then
that all?
Then after I kind of feel that everybody went through this and then understood and feeling very comfortable, then I'm going to tell you, okay, turn in those.
No, is A11 and A1-2 A1-2.
This is a unit A1 homework assignment. It's a one block. Right. Any other question? Have a great day. And we're going to see you back on Friday.
I think what you meant to say is are A1 and A2 due at the same time individually, and as you said, they're due separately.
Those
Yeah, or the.
Yeah, those are one block. So I'm gonna probably ask you to turn it into A1. Yeah. Of course, you have a file folder already set for A1. So everything A1 goes into that file.
So you can kind of do the homework in groups based on the units on there, like all of A1s together, all of A2s together. Okay.
That's right.
Got it.
I'm gonna just text you, but I'm gonna do it based on the.
Let me stop recording.